Hello, and a soft welcome to the Midnight Scientists. If you have found your way to this quiet corner of the universe, you are likely seeking a gentle current to carry you away from the day. And what better way to drift than with a slow, calming dive into the silent, invisible world of chemistry? Tonight, we will not be dealing with loud reactions or jarring discoveries. Instead, we will journey into the quiet elegance of atoms bonding in the velvet dark, to the barely audible hum of molecules in their constant, gentle motion. Our exploration is about the invisible forces that shape everything you touch, taste, and tiptoe around in the stillness of your room. My voice will be your steady guide, and I will do my best to keep our path soothing and smooth. But I must offer a fair warning. The universe is a place of profound and gentle fascination. I hope this journey is not so interesting that it keeps you wide-eyed and alert. But if it does, well, at least you'll drift toward your dreams a little wiser than before. Before we begin our gentle descent into this molecular world, if you find comfort in this kind of calm, curious content, a gentle press of the like button or a quiet subscription would be truly appreciated. It helps this little sanctuary of science remain a cozy and peaceful place. And if you feel so inclined, feel free to share in the comments where in the world you're listening from and what time the clock shows for you right now. It is a quiet joy to see how far these sleepy science stories travel across the night. Now, settle in, let your body grow heavy, let your breath find its own slow, natural rhythm. Allow the thoughts of the day to become distant clouds floating gently away. Tonight, we are going to explore why things react, bond, or sometimes just sit there in perfect stillness, doing absolutely nothing at all. Oh, and while we will be touching upon the chemistry within our bodies and brains later on, please remember that nothing in this video is intended as medical advice. It is simply friendly, fact-checked bedtime science. Imagine holding something in your hand, anything at all, a smooth stone, a soft feather, perhaps even the cool weight of a silver spoon. Now, in your mind's eye, imagine dividing that object in half, and then in half again, and again, and again, until you couldn't possibly divide it any further. You would eventually arrive at something so fundamentally tiny that it ceases to be the object you started with. It becomes something else entirely, an atom. Atoms are the silent, ancient architects of all matter. Everything that surrounds you, the pillow beneath your head, the soft fabric of your blanket, the mug you sipped from hours ago, the very screen you might be looking at, is woven from these tiny particles. In fact, you are made of atoms. You are a walking, talking, and occasionally yawning constellation of organized stardust. And while the atoms themselves are impossibly small, the science that governs them is anything but. Let us begin at the very, very beginning, in the quiet heart of it all. An atom is composed of three main types of particles: protons, neutrons, and electrons. If an atom were a miniature solar system, the protons and neutrons would be huddled together at the center, a dense and steady sun, forming what we call the nucleus. The electrons, in turn, would be the speedy, distant planets zipping around the nucleus in regions we call orbitals. Though in truth, it's not quite like planets orbiting a star. In the strange and gentle world of the quantum, electrons behave more like soft clouds of possibility than precise moving dots. They exist in fuzzy, indistinct regions where they are likely to be, but we can never know exactly where they are at any given moment. They are elusive, quiet things, like a whisper you can't quite place. The nucleus, on the other hand, is dense and central. Protons carry a positive charge, neutrons carry no charge, And together, they form the heavy, stable heart of the atom. It is the number of protons that defines what element an atom is. For instance, any atom with just one proton is always hydrogen. Any atom with 6 protons is always carbon. If you add or remove a proton, you are no longer dealing with the same element. It's a fundamental identity, a name tag assigned by the universe itself. Neutrons, while electrically neutral, serve a crucial purpose. They are the quiet diplomats of the nucleus. Without them, the positively charged protons would push each other apart with immense force. Neutrons act as a gentle buffer, a calming presence that glues the nucleus together in a state of peaceful stability. And then we have the electrons. These are the sprightly, nimble ones. They carry a negative charge and exist in various energy levels or shells around the nucleus. The farther an electron is from the nucleus, the more energy it holds, like a kite flying higher and higher in a gentle breeze. Electrons are the social messengers of the atomic world, constantly darting, shifting, and occasionally leaping to higher energy states when they absorb a bit of energy, perhaps from heat or light, before releasing it again as they fall back into a state of rest. But here is where the story becomes even more intriguing. Atoms are almost entirely empty space. If an atom's nucleus were the size of a single pea placed in the middle of a vast cathedral, the nearest electron would be a tiny speck of dust floating somewhere near the high ceiling. This means that everything you perceive as solid, your own body, the bed you are resting on, is composed of minuscule particles suspended in vast, silent voids of nothingness. Matter feels solid not because it's packed tightly with substance, but because of the invisible forces that hum between these particles. It's like standing in a room full of invisible, soft walls. You cannot see them, but you can feel where they begin and where they end. Each atom is incredibly small, about 1/10,000,000th of a meter across. To offer a sense of scale, a single grain of sand contains more atoms than there are stars in the known observable universe. And yet, every single one of those countless atoms plays by the same fundamental rules, following the same quiet choreography of attraction, repulsion, and bonding. When these atoms come together, they form molecules, which can then build just about everything: gases, liquids, solids, stars, and you. But even on its own, a single atom tells a fascinating story. Take helium with just 2 protons, 2 neutrons, and 2 electrons. It's light, unreactive, and a bit aloof. It prefers not to bond with other atoms, content to float solo, quite literally. Then you have oxygen, a far more social type, always looking to pair up, ready and willing to form bonds that are essential to nearly every breath you take. You could almost imagine these atoms at a quiet cosmic gathering. Helium would be off in a corner, perfectly content in its solitude, while oxygen and hydrogen are on the dance floor, gracefully combining to form water. Of course, not all atoms are stable. Some are radioactive, their nuclei a bit too heavy or unbalanced for their own good. They decay over time, gently breaking apart and releasing energy in the process. It's a slow, transformative end for something so tiny, and yet this process powers everything from the core of our planet to distant stars. Even instability has its own quiet role to play in this vast atomic drama. What is truly remarkable is how predictable and orderly all of this is. Through centuries of quiet observation and experimentation, we can now understand how atoms behave with incredible accuracy. We can map their configurations, predict their interactions, and even gently guide them to build entire new materials. It is the universe's ultimate blueprint, one that requires no instructions, just a deep and patient understanding of the rules. These atoms, with all their unique personalities, make up the periodic table, that beautifully ordered grid of elements. Each square represents a different kind of atom, a different character in the story of the universe. Some are gregarious and bond easily. Others are solitary and reserved. Some are heavy and slow. Others are light and reactive. The table is more than a scientific chart. It's a cast of characters for the fundamental play of existence. And though we have come to understand so much, atoms remain filled with a gentle wonder. They obey the strange, dreamlike rules of the quantum, where particles can exist in multiple states at once, and where the simple act of observing something can change its behavior. It is science at its most poetic and its most deeply perplexing. Atoms do not think or feel, of course. They have no awareness that we are speaking of them now. But if they did, perhaps they would be amused to know that these tiny, invisible bits of existence are the stars of the entire show. Quietly, invisibly, they shape everything, including the thoughts we are thinking, the dreams we are dreaming, and the very breaths we are taking right now. So here we are, nestled in a world built from countless tiny somethings, most of which is empty space, all dancing to laws they have followed for billions of years. And yet, somehow, in all that stillness and emptiness, life emerges, consciousness emerges, you emerge, and it all begins with the atom, the smallest something that makes up everything. Now that we've met the quiet, steady heart of the atom, let's turn our attention to its more energetic and unpredictable companions, the electrons. These tiny, zippy, wonderfully elusive particles are somehow responsible for nearly every chemical interaction you've ever witnessed. Electrons may be the lightweights of the atomic world, nearly 2,000 times less massive than a single proton, but what they lack in heft, they more than make up for in influence and energy. Electrons don't behave in ways we might intuitively expect. In fact, the deeper you drift into their world, the more strange and dreamlike things become. If protons and neutrons are the dependable, stoic guardians of the nucleus, electrons are more like fleeting thoughts or flashes of inspiration. They are constantly moving, impossible to pin down, and are the source of all the drama and connection in the chemical world. Let's begin with the basics. Electrons carry a negative electric charge, and they are drawn toward the positively charged protons in the nucleus, much like a night-flying moth is drawn to a soft, distant light. This gentle attraction is what keeps them from drifting off into the void, but it doesn't mean they settle down quietly. Electrons are in constant motion, and their behavior is best described not by a neat, predictable orbit, but by something far more ethereal, the probability cloud. In our everyday world, you can describe exactly where an object is and where it is going. But electrons belong to the quantum realm, where concepts like location and momentum are soft and hazy. Instead of a clear path, scientists describe an electron's presence as a fuzzy cloud of probability, a region where it is most likely to be found at any given moment. The denser the cloud, the higher the chance the electron is hovering in that spot. It's a bit like searching for a sleeping cat in a quiet house. You don't know its exact location, but based on past experience, you know it's probably curled up in a patch of moonlight by the window or nestled in the warmth of a soft blanket. These clouds, known as orbitals, come in different shapes and sizes. Some are simple spheres, some are shaped like dumbbells, and others possess even more intricate, beautiful forms. Orbitals are grouped together in layers called shells, which are arranged around the nucleus like the delicate layers of an onion. Each shell can hold a specific number of electrons. The first, innermost shell holds up to 2, the second holds up to 8, the third up to 18, and so on. Electrons, seeking stability, prefer to occupy the lowest available energy levels first, only moving to higher shells when the lower ones are full or when they absorb a little extra energy. And here is where the story of connection truly begins. An atom's desire to interact with the world depends almost entirely on its outermost electrons, also known as the valence electrons. These are the electrons in the atom's highest energy shell, and they are the ones that will reach out and interact with other atoms. If an atom's outer shell is completely full, it tends to be stable, serene, and unreactive. It is content, like someone who is already comfortably wrapped in a warm blanket with a soothing cup of tea. But if that outer shell is incomplete, the atom becomes restless. It starts looking for ways to gain, lose, or share electrons to find that state of contentment. And this is where all the bonding begins. Consider the noble gases, like helium or neon. Their outer shells are perfectly full. As a result, they barely interact with other atoms. They are the quiet introverts of the chemical world, perfectly happy in their own company. Then you have elements like sodium, which has just one lonely electron in its outer shell. That electron is loosely held, ready to find a new home, allowing the atom to achieve a more stable, complete inner shell. On the other side of the periodic table, you find chlorine, which is just one electron short of a full outer shell. It would love nothing more to welcome an extra one to complete its set. When sodium and chlorine meet, it is a perfect match. Sodium gracefully donates its extra electron to chlorine. In doing so, both atoms achieve the stability they were seeking. Together, they form sodium chloride, ordinary table salt. And just like that, a quiet connection is formed. This gentle drive for a full outer shell, often called the octet rule, is the primary motivation behind why atoms form bonds. They will do almost anything, share electrons, give them away, or accept them just to find that peaceful, stable configuration. Sometimes it's a fair and mutual sharing, as in covalent bonds, where atoms contribute electrons equally. Other times, it is more of a complete and graceful transfer, as in ionic bonds, where one atom gives up an electron entirely and another accepts it. Energy also plays a beautiful role in the life of an electron. When an atom absorbs energy from light or heat, its electrons can become excited. An excited electron absorbs this energy and makes a brief energetic leap to a higher shell, farther from the nucleus. It doesn't stay there for long, however. Electrons, like all things in nature, seek the lowest, most stable energy state. And so, before long, the excited electron will fall back to its original lower energy level. As it does, it releases that extra energy, often as a beautiful, tiny flash of light. Electrons are also the reason metals possess their characteristic shine and ability to conduct electricity. In a piece of metal, the outer electrons aren't tied to any single atom. Instead, they can move freely throughout the entire structure, forming a kind of communal cloud, a silent, flowing river of charge. These free-moving electrons reflect light, giving metals their beautiful luster, and they allow an electric current to flow smoothly through them. In the grand story of chemistry, electrons are the ultimate matchmakers, the quiet diplomats, and the gentle instigators of change. Their behavior determines whether atoms will bond, what kind of bond will form, how strong that bond will be, and how easily it can be broken. The number and arrangement of electrons affect how substances look, feel, and behave. Whether something is a gas, a solid, or a liquid depends, in part, on how tightly electrons hold atoms together. Whether something is shiny or dull, conductive or insulating, it is the electrons that are quietly pulling the strings. Even the colors we see are a result of electrons interacting with light. The pigments in a ripe red strawberry appear that way because their electrons absorb most other colors of light but reflect the red wavelengths back to our eyes. The deep blue of the evening sky, the soft green of new leaves, it is all a silent story told by electrons absorbing, emitting, and interacting with light in their own beautifully peculiar ways. What is perhaps most mind-bending is that we still do not fully understand them. Electrons are governed by the strange and wonderful rules of quantum mechanics, a field so counterintuitive that it often feels more like poetry than physics. Electrons can behave as particles or as waves, or sometimes as both at once. They can exist in multiple places until observed. They are slippery, mysterious, and utterly essential to the chemistry of life. In the end, though they are unimaginably small, electrons are the restless hearts of all atoms, always in motion, always influencing the world around them. From the bonds that hold our world together to the sparks of thought that flicker through our minds, electrons are responsible. They are the quiet agitators, the energetic instigators, the invisible artists behind the patterns of reality. Each thought that drifts through your mind right now is an electrical signal carried by electrons fluttering through your neurons like tiny, fleeting flashes of consciousness. Small, yes. Shifty, definitely. But without them, the universe would be a very dull and very dark place indeed. If atoms have personalities, then chemical bonds are their relationships. Some are clingy and inseparable, some are generous and giving, and some prefer a more free-flowing, communal arrangement. But no matter how different they seem, all bonds form for the same fundamental reason: to achieve a state of greater stability. Atoms are constantly seeking a lower, more peaceful energy state, and forming a bond is the surest way to get there. It is a quest not of emotion, but of a deep, logical desire for balance. Let's begin with the most classic of atomic pairings, the covalent bond. Picture two people quietly sharing a warm blanket. It's not a struggle, but a fair, mutual sharing that benefits both. That is the essence of covalent bonding. Two atoms each contribute an electron to the relationship, and together they share the pair. It's a peaceful, stable arrangement where everyone contributes and everyone benefits. Covalent bonds are especially common among nonmetals. Oxygen and hydrogen, for example, come together to form water by sharing electrons. Each hydrogen atom brings one electron to the partnership, and oxygen brings two of its own to share. Together, they complete their outer shells, fitting together like perfect, interlocking puzzle pieces. This bond is not just functional, it is foundational. The structure of water, created by these shared bonds, gives it all of its unique and life-sustaining properties, all thanks to atoms politely sharing. But not all relationships are built on sharing. Sometimes one atom desires an electron so strongly that it simply accepts it from another. This is where ionic bonds come into play. Instead of sharing, one atom gracefully donates an electron and the other gratefully accepts it. In this process, both atoms become electrically charged ions. The atom that loses an electron becomes positively charged, while the one that gains an electron becomes negatively charged. These oppositely charged ions are then drawn to each other by a powerful electrostatic attraction, like two magnets gently clicking into place. We saw this with sodium and chlorine. Sodium has one lonely electron it is eager to give away to find stability. Chlorine is just one electron short of a full shell and longs to complete its set. Sodium hands over its electron, and chlorine triumphantly accepts it. They transform into a sodium ion and a chloride ion, stick together, and become sodium chloride, or as it's known in kitchens around the world, table salt. In ionic bonding, there is no sharing. It is a full and complete transfer. The resulting ions are strongly attracted to one another, forming solid, crystalline structures. These are the neat, geometric stacks that make salt crystals sparkle so beautifully under the light. Then there is a third, very different kind of social dynamic. Picture a quiet, communal library where everyone has placed their books on a central table for all to share. No one keeps track of which book belongs to whom. They are all available for the good of the community. That is metallic bonding in a nutshell. In metals, the atoms don't just bond with their immediate neighbors. Instead, their outer electrons become delocalized. They are free to wander throughout the entire metallic structure, forming a sea of electrons that flows between the positively charged metal ions. This shared electron sea is what gives metals their characteristic properties. Because the electrons can move so freely, metals conduct electricity with ease. This same fluidity is responsible for their shiny, reflective surfaces and their ability to be shaped without breaking, a property known as malleability. But why do atoms go to all this trouble? The simple answer is energy. Every atom seeks to be in the lowest possible energy state, and bonding is one of the best ways to achieve that. When atoms form a bond, they release energy, moving from a higher energy solo existence to a lower energy bonded state. It is the atomic equivalent of finally sinking into a comfortable chair after a long day. At last, everything is calm and stable. The outermost electrons, those valence electrons, are the matchmakers in this whole scenario. Atoms are most reactive when their outer shells are incomplete. A hydrogen atom with just one electron wants to find a partner. A fluorine atom missing just one is eager to pair up. These needs are what drive atoms to seek out others, forming connections that satisfy both. Sometimes these bonds are incredibly strong. Diamonds, for instance, are a lattice of carbon atoms held together by a rigid, three-dimensional network of covalent bonds. This structure is what creates one of the hardest materials known to humanity. On the other hand, some bonds are quite gentle, like the attractions between water molecules. These are called hydrogen bonds. They are not full-fledged chemical bonds, but they are strong enough to give water its high boiling point and its remarkable surface tension, allowing insects to walk across its surface as if on a thin, invisible film. The strength of a bond is influenced by an atom's electronegativity, a measure of how strongly it pulls on electrons in a bond. An element like fluorine is famously greedy. It has the highest electronegativity and will pull shared electrons closer to itself in any covalent bond. On the other hand of the spectrum, atoms like cesium are far more relaxed about electron custody. When bonds form, energy is usually released in a process called an exothermic reaction. When bonds are broken, energy must be absorbed, which is an endothermic reaction. That's why lighting a fire requires an initial spark. You need to input energy to break the bonds in the wood. But once they break and new, more stable bonds form in the resulting smoke and ash, a flood of energy is released as heat and light. The world around you is held together by these countless, invisible bonds, each one a result of atoms seeking peace and stability. Your own body is a vast, ongoing symphony of chemical bonding. Proteins fold into precise shapes. DNA strands are held together by gentle attractions. Even your thoughts are made possible by ions moving across cell membranes. At the end of the day, bonding is chemistry's way of creating order from chaos. Whether atoms share evenly, transfer outright, or contribute to a communal pool, the goal is always the same: lower energy, greater stability, and the potential to build something new. A gas becomes a liquid, a spark becomes a flame, all because of the endless ways atoms can link, rearrange, and hold on to one another. It is a silent, ceaseless dance of give and take, of holding hands and sometimes letting go. Energy is the quiet heartbeat of every chemical reaction. It's the invisible currency traded between atoms as they form or break bonds, reshape themselves, or transform into something entirely new. But even the most reactive substances usually need a gentle push to get started. This little nudge is what chemists call activation energy, the minimum amount of energy required to initiate a reaction. Without it, even the most promising combination of ingredients would simply sit together in an awkward silence, like two people at a quiet party waiting for someone else to speak first. Consider a matchstick. It contains all the necessary ingredients for fire: chemicals eager to react, oxygen in the air, and a wooden stick ready to be transformed. And yet, nothing happens. That gentle friction provides the activation energy needed to kickstart the reaction. A little heat is introduced, molecules begin to vibrate more vigorously. Old bonds start to stretch and break, and new ones quickly form. In the blink of an eye, combustion begins. But without that initial spark, the match would remain perfectly still. That's because molecules, in their natural state, prefer to remain as they are, unless something comes along to jostle them out of their comfort zones. Activation energy is that gentle, or sometimes not so gentle, nudge. You can picture activation energy as gently pushing a boulder over a hill. The boulder represents your reactants, resting comfortably at the base. To get to the other side, the product side, the boulder must first be pushed uphill. That uphill effort is the activation energy. Once the boulder reaches the peak, it can roll down the other side with ease. Similarly, once a reaction overcomes its energy barrier, it tends to proceed without much additional effort. Some reactions need very little energy to begin, while others require a great deal. This is why certain chemicals can sit safely on a shelf for years, while others might burst into flame at the slightest provocation. It's not just about what the molecules can do, but how much energy it takes to convince them to do it. Now, let's explore what happens after a reaction gets started. Once those initial bonds begin to shift, energy is either absorbed or released. This brings us to two important types of reactions: endothermic and exothermic. Endothermic reactions are those that absorb energy from their surroundings. It's like the reaction needs a steady diet of heat to keep going. The classic example is photosynthesis, the process by which plants use sunlight to convert carbon dioxide and water into glucose. Without that constant stream of solar energy, the entire process would grind to a halt. Another example of an endothermic process can be found in instant cold packs. These contain water and a separate pouch of a salt like ammonium nitrate. When the two are mixed, the dissolving process absorbs heat from the surroundings, rapidly lowering the temperature. The cold you feel isn't something being created by the reaction, it's the sensation of heat being drawn away from your skin. On the other side, we have exothermic reactions, the warm, generous types that release energy into their surroundings, usually as heat or light. Combustion is the most dramatic example. When you light a candle, you are watching hydrocarbons in the wax react with oxygen to produce carbon dioxide, water vapor, and a steady, satisfying release of heat and gentle flame. Fireworks, explosions, and even the metabolism of food inside your body are all driven by exothermic reactions. In fact, your cells are like tiny, polite combustion chambers. When you eat, the sugars in your food are broken down in a controlled, step-by-step series of exothermic reactions. This releases the energy your body uses for everything from blinking to dreaming. You don't burst into flame, thankfully, because the energy is released in small, manageable doses, carefully regulated by enzymes. Some reactions can go either way. Water evaporating from a surface is endothermic. It absorbs heat to escape into the air as vapor. But when that vapor condenses back into liquid, as dew on the morning grass, it releases that heat in an exothermic process. These reversible reactions create a sort of energetic dance, shifting depending on the surrounding conditions. Interestingly, many reactions that seem explosive are really just very fast. A pile of dry leaves slowly decomposing over many months is a chemical reaction. The same leaves set ablaze transform in seconds. Both processes involve rearranging the same atoms, but one takes a leisurely, quiet path, while the other charges ahead in a fiery burst of exothermic enthusiasm. Catalysts can influence this process by lowering the activation energy. These are substances that speed up a reaction by providing an easier path, making it simpler for reactants to reach that tipping point. They are the quiet matchmakers of the chemical world, gently encouraging bonds from behind the scenes without getting involved themselves. Enzymes in your body are biological catalysts that make the chemistry of life possible. Without enzymes, the reactions in your body would be so sluggish that you couldn't survive. Digestion would take years instead of hours. Catalysts don't provide the energy themselves, they simply make the journey smoother and faster. The idea of activation energy also helps us understand why some substances are unstable. If a molecule is already perched precariously in a high-energy state, it may only need the smallest nudge to collapse into something more stable, releasing energy in the process. This is the case with many reactive chemicals. They've already paid most of their activation energy fee and are just waiting for the door to open. So many safety measures revolve around controlling this energy threshold. Volatile chemicals are stored in cool, dark places to minimize the available energy. It's why medicines are often refrigerated and aerosol cans carry warnings about heat. It all comes down to managing energy on a molecular level. In a way, all chemical reactions are just nature's method of reorganizing atoms to find a more comfortable energy level. It's not unlike adjusting your pillows before you fall asleep, shifting things around until everything feels just right. Whether it's the gentle warmth of a hand warmer, the cool sensation of a cold pack, or the soft glow of a candle, you are witnessing the quiet play of energy, moving, transforming, and occasionally bursting forth. It is never random. There is always a reason, and that reason almost always involves just the right amount of energy, arriving at just the right moment. Acids and bases are the great mood setters of the chemical world. When they enter a solution, things tend to become quite lively. They can make metals fizz, change the color of liquids, or turn simple cabbage juice into a beautiful chemistry experiment. And while we often think of them as opposites, they are really just two sides of the same reactive coin, both defined by how they interact with water and, more specifically, with two very important ions, hydrogen ions, H+, and hydroxide ions, OH-. To understand them, let's start with pure water. Water, though it seems perfectly neutral and peaceful, is in a constant, quiet state of flux. At any given moment, a tiny fraction of water molecules spontaneously separate into H+ and OH- ions. Then, just as quickly, they recombine to form water again. It's a delicate, balanced equilibrium, like a calm, whispered conversation in a room full of molecules. Now, an acid is any substance that increases the concentration of hydrogen ions, H+, when added to water. You can think of it as a generous donor, always handing out H+ ions to the solution. On the other hand, a base is a substance that either removes those H+ ions or adds hydroxide ions, OH-. In essence, acids tilt the balance toward more H+, while bases tilt it toward more OH. This balance is measured using the pH scale, which typically ranges from 0 to 14. A pH of 7 is considered perfectly neutral. This is the pH of pure water, right in the middle. Anything with a pH below 7 is acidic, and anything above 7 is basic or alkaline. The lower the number, the more acidic the solution. The higher the number, the more basic. It's important to remember that the scale is logarithmic, which means each whole number represents a tenfold difference. So, a solution with a pH of 4 is 10 times more acidic than one with a pH of 5. Lemon juice with a pH around 2 is quite acidic. Vinegar sits around pH 3. On the other side of the scale, baking soda is mildly basic, around pH 9, while household bleach can be highly alkaline with a pH of 12 or 13. At these extremes, both strong acids and strong bases can be quite corrosive. Chemically, what makes an acid so reactive is its tendency to release those hydrogen ions. These tiny, positively charged particles, once freed in a solution, can interact with other molecules in all sorts of ways, altering their structures, speeding up reactions, or even damaging tissues. Bases, meanwhile, either absorb those free hydrogen ions or contribute hydroxide ions that neutralize them. This constant tug of war over H+ ions is at the heart of countless chemical processes. Acids and bases are everywhere. In your stomach, hydrochloric acid helps digest food by breaking down proteins. Your body then releases bicarbonate, a mild base, to neutralize that acid as the food moves on. In cooking, acids like lemon juice or vinegar add brightness and flavor. They can also tenderize meat by denaturing its proteins. Bases are less common in the kitchen, but they have their uses too. Baking soda, a base, reacts with an acid, like buttermilk, to release carbon dioxide gas, causing dough to rise and become light and fluffy. One of the most satisfying demonstrations of this chemistry is neutralization. When an acid and a base meet in just the right amounts, they react to form water and a salt. This can happen subtly or, as with the classic vinegar and baking soda volcano, with a great deal of enthusiastic bubbling. That fizz is the release of carbon dioxide gas, a harmless, visible sign of a peaceful resolution between chemical opposites. The way acids and bases affect reactions goes far beyond simple fizzing. They can change the structure of molecules and act as catalysts or inhibitors. In living organisms, this sensitivity to pH is crucial. The enzymes in your body are highly dependent on pH. If their environment becomes too acidic or too basic, they can lose their shape and stop working. This is one reason why your body works so hard to maintain your blood pH in a very narrow, stable range, around 7.4. Just a small shift can cause serious health problems. pH also plays a significant role in the environment. Acid rain caused by pollutants in the atmosphere can lower the pH of lakes and soils, harming plant and aquatic life. Similarly, ocean acidification caused by the absorption of excess carbon dioxide from the air affects the ability of marine creatures like corals and shellfish to build their protective shells. These might seem like small shifts, but in systems finely tuned over millions of years, they can have cascading effects. In industry, acid-base chemistry powers everything from wastewater treatment to the lead-acid batteries in cars. In cleaning products, bases help to dissolve grease and grime. It's not magic, it's just hydrogen and hydroxide ions doing their usual quiet dance. Indicators are another charming part of this toolkit. These are substances that change color depending on the pH. Litmus paper turns red and acid and blue and moist. Even red cabbage juice can act as a natural pH indicator, shifting through a beautiful rainbow of colors depending on a solution's acidity. But behind all the colorful transformations lies a deep and elegant system that governs countless processes in our bodies, our environment, and our technology. At its heart, acid-base chemistry is all about balance, the push and pull between giving and taking, between too much and not enough. One offers, the other accepts, and in just the right proportions, they find peace, a stable, neutral place where the fizzing stops and the chemistry settles down, at least until someone adds a little more lemon juice. Temperature and pressure might seem like things you simply adjust on a thermostat or check in a weather report, but in the world of chemistry, they are master manipulators. They are the invisible forces that can coax molecules to dance, collide, and react, sometimes slowly and gently, other times with explosive speed. They are the ultimate party planners for the molecular world, setting the scene and the energy level for reactions to begin. To understand how this works, we can turn to one of the most important ideas in chemistry, the kinetic molecular theory. At its heart, this theory states that all matter is made of particles in constant, ceaseless motion. Even in something that appears perfectly still, a block of ice, a wooden table, your own fingertips, the atoms and molecules within are vibrating, jiggling, and bouncing in place. The hotter a substance is, the faster its particles move. The cooler it is, the slower and more gentle their jiggle. Imagine a quiet, spacious room full of people slowly wandering. They might rarely bump into one another. But if you were to play some lively music, the energy in the room would rise. People would start moving faster, and the chance of collisions would increase significantly. The same is true for molecules. Heat is a form of energy, and when you add it to a system, its particles gain kinetic energy. They move faster, they collide more often, and they collide with greater force. Since chemical reactions happen when molecules collide in just the right way with enough energy, heating a substance dramatically increases the likelihood that a reaction will occur. This is why food cooks faster in a hot oven and why milk spoils more quickly on a warm day. Heat, quite literally, gets things moving. However, not every collision results in a reaction. Molecules must collide with sufficient energy, the activation energy, and at the correct orientation. It's like tossing two puzzle pieces at each other. Only when they hit in just the right way will they snap together. The added energy from heat helps more of those collisions to be successful ones. Now, let's bring pressure into the picture. Pressure is all about how tightly particles are squeezed together. This is especially important for gases, where molecules are naturally far apart and moving freely. If you increase the pressure, you are forcing those molecules into a smaller space, cramming them closer together. With less room to roam, collisions become far more frequent, which in turn increases the rate of reaction. Think of it like a crowd at an outdoor concert in a wide open field versus the same crowd packed into a small club. In the club, people will be brushing shoulders constantly. In chemistry, those shoulder bumps are opportunities for reaction, and pressure makes them happen more often. Temperature and pressure don't just affect the speed of reactions, they can also influence which products are formed. Some reactions will only occur at very high temperatures or under extreme pressure. Others might even reverse direction if the conditions are changed. This is critically important in industrial chemistry, where fine-tuning heat and pressure can maximize the yield of a desired product. A famous example is the Haber-Bosch process, which produces ammonia for fertilizer from nitrogen and hydrogen gases. On their own, these gases have little interest in reacting, but under high temperature and very high pressure, with the help of a catalyst, they are finally convinced to combine and form ammonia. This single, carefully controlled reaction is now responsible for a significant portion of the world's food supply. Temperature also changes the nature of substances themselves through phase changes. Solids melt into liquids, and liquids evaporate into gases as particles gain enough energy to overcome the forces holding them together. These transitions are physical, not chemical. The molecules themselves remain the same, but they demonstrate the powerful ability of heat to disrupt structure and enable new kinds of motion. Pressure has its own quirks as well. While it primarily affects gases, it can also influence reactions involving liquids and solids, especially if the reaction involves a change in volume. According to Le Chatelier's principle, if a reaction produces fewer gas molecules than it started with, increasing the pressure will favor the forward reaction, as the system tries to relieve that pressure. This interplay between heat and pressure appears in countless everyday experiences. A pressure cooker works by trapping steam, which increases the internal pressure and raises the boiling point of water. This allows food to cook at a higher temperature, making it faster and more tender. At the bottom of the deep sea, the immense pressure changes the way gases dissolve and how chemical reactions proceed, allowing unique forms of life to thrive near hydrothermal vents. In the lab, chemists manipulate these variables with great precision, but managing them is a delicate art. Too much heat can cause sensitive compounds to decompose. Too much pressure can become a serious engineering challenge. Sometimes the goal isn't speed at all, but control, allowing a reaction to proceed slowly and predictably to avoid unwanted side products. What's remarkable is how universal these principles are. Whether you are baking bread, studying volcanoes, or designing rocket fuel, the same basic rules apply. Heat adds motion, pressure adds proximity, and together they influence the course of chemistry in ways both subtle and spectacular. So much of what we observe is shaped by these invisible forces acting on tiny particles. Molecules don't decide to react, they are guided by energy, movement, and proximity. Heat gives them the speed, and pressure gives them the squeeze. Together, they unlock the endless possibilities of transformation, one gentle collision at a time. In the neat and tidy world of textbooks, chemical reactions often look like one-way streets. You begin with reactants, you mix them, and products appear. The reaction is done. But in reality, chemistry is rarely so final. Many reactions can in fact go both ways. Molecules don't just combine and call it a day. They can also separate, rejoin, and sometimes drift back and forth between states endlessly. This is the world of reversible reactions, where the finish line is more of a gentle roundabout than a dead end. A reversible reaction is exactly what it sounds like, a chemical process that can proceed in both the forward and reverse directions. Reactants become products, but those very products can also break down to become reactants again. It's a chemical tug-of-war where both sides are pulling and neither ever wins. Instead of one side collapsing, the system settles into a state of balance, a kind of truce. This peaceful balance is called chemical equilibrium. Equilibrium doesn't mean that nothing is happening. On the contrary, the reaction is still occurring in both directions, but it's doing so at exactly the same rate. Imagine people walking up an escalator at the same speed as people are walking down it. The number of people at the top and the bottom remains constant, even though there is perpetual movement. This is a dynamic equilibrium. This concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart. The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remains constant. This dynamic equilibrium concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart. The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remains constant. Equilibrium doesn't mean that nothing is happening. On the contrary, the reaction is still occurring in both directions, but it's doing so at exactly the same rate. Imagine people walking up an escalator at the same speed as people are walking down it. The number of people at the top and the bottom remains constant, even though there is perpetual movement. This is a dynamic equilibrium. This concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart. The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remain constant. This equilibrium is a delicate state, dependent on temperature, pressure, and concentration. This is where a helpful piece of chemical wisdom comes in, known as Le Chatelier's principle. It states that when you disturb a system at equilibrium, the system will shift in a way that counteracts the disturbance. It's surprisingly intuitive. Imagine a room with a thermostat set to a comfortable temperature. If someone opens a window and cold air rushes in, the heating system kicks on to bring the temperature back up. Chemical systems behave in a similar way. If you add more reactants to a system at equilibrium, the reaction will shift to use them up, producing more products. If you remove products, the system will shift to replace them. If you increase the heat, the system will shift in the direction that absorbs heat, the endothermic direction. It is constantly adjusting, trying to undo whatever change was introduced. Pressure works the same way, especially with gases. If you increase the pressure, the system will shift toward the side of the reaction with fewer gas molecules in an attempt to reduce the crowding. It's all a matter of balance, of molecules trying to find the most comfortable arrangement under their current circumstances. Equilibrium is especially important in biological systems. Our bodies rely on countless reversible reactions that must remain finely tuned. Take the oxygen-carrying protein hemoglobin. In the lungs, where oxygen concentration is high, the equilibrium favors binding, and oxygen attaches to hemoglobin. In the tissues, where oxygen levels are lower, the equilibrium shifts and hemoglobin releases the oxygen where it is needed. It's an elegant, automatic adjustment that happens with every single breath. Another vital example is the carbonic acid equilibrium in our blood, which helps maintain our blood pH within a very narrow, stable range. Your body uses this reversible system, along with your lungs and kidneys, to remain in a state of perfect chemical harmony. In industrial chemistry, mastering equilibrium can mean the difference between success and failure. The Haber-Bosch process for making ammonia, for instance, is a reversible reaction. By carefully manipulating the temperature and pressure, chemists can shift the equilibrium to favor the formation of the desired product, ammonia. It's a constant balancing act between chemistry and efficiency. There is something poetic about equilibrium. It reminds us that nature often prefers moderation and compromise over extremes. The world isn't full of reactions that go in one direction and simply stop. Instead, it is full of reversibility, of systems that adjust, respond, and settle into a state where everything seems calm on the surface, even as there is constant motion underneath. Even in a bottle of vinegar on your kitchen shelf, tiny equilibrium shifts are still occurring. In the atmosphere, gases are constantly exchanging and reacting. Even in solid rocks, over vast geological timescales, minerals transform and equilibrium slowly drifts from one state to another. Equilibrium is a dynamic pause, a point where change doesn't cease, but rather balances itself out. It's the moment when the tug-of-war rope stops moving, not because the pulling has stopped, but because both sides are pulling with equal, gentle force. It is not peace through stillness, it is peace through motion. And remembering this, you start to notice balance everywhere, in chemical reactions, in ecosystems, and in the quiet rhythm of your own breath. Explosions are chemistry's most dramatic and sudden outbursts. They are the grand, showy spectacles that demand attention, fast, fiery, and loud. But behind the startling booms and brilliant flashes of light lies a surprisingly elegant principle: the extremely rapid release of energy from a chemical reaction. An explosion is simply chemistry happening at an incredible speed, often in a confined space, with very little regard for subtlety. At its core, an explosion is a sudden, rapid expansion of matter accompanied by a release of energy, as heat, light, and shock waves. The key ingredient is always speed, reactions that happen in milliseconds, unleashing enormous amounts of energy all at once. Most chemical explosions involve combustion, where a substance reacts quickly with an oxidizer like oxygen. Combustion isn't always explosive, but the gentle flame of a candle is a controlled, steady burn. But if you change the conditions, add more fuel, more oxygen, or confine it tightly, the very same chemistry can become explosive. Imagine a simple balloon filled with hydrogen gas. If you introduce a spark, the hydrogen will rapidly react with the oxygen in the air to form water vapor. This reaction is extremely exothermic, releasing a large amount of energy so quickly that the surrounding air expands almost instantly, creating a shock wave we hear as a loud and satisfying bang. The key to most explosions is this rapid oxidation. In a slow burn, like rusting, the energy is released gradually and dissipates. In an explosion, it's unleashed all at once, like a tightly wound spring suddenly being let go. Fireworks are a perfect example of how controlled explosions can be used to create beauty. Each firework is a carefully packed chemistry lab containing fuels, oxidizers, and color-producing metal salts. When ignited, the fuel burns rapidly, producing hot gases that propel the firework into the sky. When it bursts, different metal salts create the vivid colors: strontium for red, barium for green, and copper for blue. It is chemistry as a carefully choreographed ballet of light and sound. Then there are high explosives like TNT, trinitrotoluene. TNT is an example of a compound that contains both the fuel and the oxidizer within the same molecule. When detonated, it rearranges its own atoms with incredible speed, producing various gases and an enormous release of heat. What makes TNT interesting is its stability. It needs a smaller, more sensitive explosive, a detonator, to provide the precise jolt of activation energy required to start the reaction. Once started, however, the reaction propagates through the material in an instant. But explosions aren't always intentional. Sometimes they are the result of accidents, when the right ingredients come together under the wrong conditions. Believe it or not, even simple kitchen ingredients can be surprisingly energetic. Fine powders like flour or powdered sugar, when suspended in the air, can form a combustible dust cloud. The tiny particles have a huge surface area, making them highly reactive. If this cloud is confined and finds an ignition source, it can result in a dangerous dust explosion. Aerosol cans contain flammable propellants under pressure. If heated, the internal pressure can build until the can ruptures, releasing the flammable gas, which can then ignite. Even adding water to a grease fire can be disastrous. The water flashes into steam, expanding rapidly and ejecting the burning oil into a massive fireball. And then there's the classic reaction between baking soda and vinegar. While not truly explosive, it is certainly enthusiastic. The acid and base react to produce carbon dioxide gas, which expands quickly, causing the familiar bubbling and fizzing. It's a gentle reminder that even simple ingredients hold reactive potential. In other settings, explosive reactions are harnessed for practical use. Car airbags deploy using a controlled, rapid decomposition of a chemical like sodium azide. This reaction produces nitrogen gas, which inflates the airbag in less than a tenth of a second, providing a life-saving cushion. Explosions even play a role in the natural world. Volcanoes are perhaps Earth's most dramatic chemists, combining heat, pressure, and reactive gases to produce massive eruptions. It's a reminder that the Earth itself is always reacting, simmering, and sometimes bursting at the seams. Ultimately, explosions are not inherently bad. They are simply fast reactions, doing what reactions do: breaking bonds, forming new ones, and releasing energy. The challenge lies in managing them. Too slow, and the reaction fizzles out. Too fast, and it can become destructive. Chemists and engineers have learned to walk this fine line, harnessing this powerful chemistry to launch spacecraft, save lives, and create moments of breathtaking beauty in the night sky. The same principles apply whether you are lighting a candle or igniting rocket fuel. It's all about energy, molecules, and the rate at which change unfolds. Carbon is the undisputed cornerstone of life's chemistry. It isn't the flashiest element, nor the heaviest, nor the rarest, but when it comes to versatility and the sheer ability to build complex and beautiful structures, carbon takes center stage. It is the molecular shapeshifter, responsible from everything from the delicate wings of a butterfly to the complex strands of your own DNA. What makes carbon so special is its unique ability to form up to 4 strong, stable bonds at once. This might not sound like much, but in the microscopic world of atoms, 4 is a magic number. It allows carbon to form an incredible variety of structures: long chains, intricate branches, and stable rings. Carbon can bond with itself and with a wide range of other elements, creating a molecular architecture that is both sturdy and flexible. This has made it the foundation for all known life. The entire field of organic chemistry is dedicated to the study of these carbon-based compounds. Carbon's talent for bonding with itself, known as catenation, is the root of its versatility. No other element can rival it. Silicon, sitting just below carbon on the periodic table, tries its best, but its bonds are weaker and less stable. Carbon is the original, and life as we know it would not exist without it. Organic molecules are essentially carbon-based frameworks decorated with functional groups, small clusters of other atoms that define how the molecule behaves. Like different accessories on a simple black dress, these groups give each molecule a specific role and personality. Add an OH group, and you have an alcohol. Add a carboxyl group, COOH, and it's an acid. It's all carbon underneath, but with different attachments, it can play almost any part. Let's talk about structure, because carbon doesn't just form molecules, it builds architecture. The simplest forms are straight chains of carbon linked in a line, but these chains can branch, bend, or even loop back on themselves to form rings, like the hexagonal structure of cyclohexane. Some molecules are enormous, like proteins, which are long, folded chains of amino acids, or DNA, which twists into its famous double helix. Others are tiny, like methane, with just one carbon bonded to four hydrogens. But no matter the size, the rules are the same. Carbon at the center, holding everything together with its four bonding arms. Those four arms also allow carbon to form double and even triple bonds with other atoms. In a double bond, two pairs of electrons are shared, creating a stronger and shorter connection. These multiple bonds change the geometry and reactivity of molecules, adding another layer of depth and complexity to organic chemistry. Then there's isomers, molecules that have the exact same chemical formula but different structural arrangements. Carbon is a master of creating isomers. It can take the same handful of atoms and arrange them in entirely different ways, leading to compounds with wildly different properties. It's a bit like rearranging the furniture in a room. The pieces are the same, but the result feels completely different. Life as we know it is essentially one long, beautiful carbon experiment. Proteins, lipids, fats, carbohydrates, and nucleic acids like DNA, the four great classes of biological macromolecules, are all carbon-based. The membranes that hold our cells together are built from lipids. Carbohydrates, like glucose, provide our bodies with quick energy. And DNA carries our genetic code in a molecule made almost entirely of carbon, hydrogen, oxygen, nitrogen, and phosphorus. All of these functions rely on carbon's ability to form bonds that are stable enough to build lasting structures, yet not so strong that they become rigid and inert. Life needs that delicate balance. It needs a scaffold that can support complexity but still allow for change, motion, and reaction. Beyond biology, carbon forms everything from the synthetic polymers in plastics to cutting-edge nanomaterials like graphene. The fuels we depend on, like gasoline and natural gas, are hydrocarbons, chains of carbon and hydrogen packed with stored energy. Carbon's versatility is also reflected in its pure forms, known as allotropes. As graphite, the carbon atoms are arranged in flat sheets, making it soft and slippery, perfect for the lead in your pencil. As diamond, the atoms are locked into an incredibly strong three-dimensional lattice, making it one of the hardest substances known. The difference is not in what they are made of, but in how the atoms are arranged. Same element, entirely different personality. And of course, carbon is the central figure in our planet's climate. Carbon dioxide, a simple molecule with one carbon and two oxygens, is a vital greenhouse gas. Its ability to trap heat has made it a focal point in our understanding of climate change and sustainability. Carbon is not just the stuff of life, it is the stuff of consequence. In the world of atoms, carbon is the quiet genius. It builds the molecules of life, the materials of modernity, and the cycles of nature. It bends, bonds, and links in ways that other elements can only dream of. It is the reason you are made of molecules instead of moon rocks. Every heartbeat, every breath, every thought comes down to this one element with four bonding arms, a love of structure, and an endless capacity for forming connections. Carbon isn't just an element, it is the storyteller of life. The word redox might sound like the name of a futuristic cleaning product, but in reality, it describes one of the most fundamental chemical processes in the universe. Short for reduction oxidation, redox reactions are all about the quiet exchange of electrons, those tiny, energetic particles that make atoms tick. Whenever something is burning, resting, charging a battery, or even digesting food, you can be sure that redox chemistry is running the show behind the scenes. At its core, a redox reaction is like a well-coordinated game of musical chairs for electrons. One substance loses electrons and another substance gains them. That's it. The trick is that these two processes, oxidation and reduction, always happen together. You cannot have one without the other. An electron doesn't just vanish. If one atom gives one up, another must be there to accept it. Here are the definitions to hold on to. Oxidation is loss of electrons, while reduction is gain of electrons. You can remember this with the acronym oil rig. It might sound counterintuitive that reduction involves a gain, but because electrons are negatively charged, gaining them reduces an atom's overall charge. Electrons are the energetic currency of atoms, and during a redox reaction, they are passed from one atom to another. Some atoms, like oxygen, are very good at pulling electrons toward themselves. Others, like metals, are more generous, readily giving up their electrons to achieve a more stable state. Let's look at a simple, iconic redox reaction, the rusting of iron. When iron is exposed to oxygen and water, it slowly transforms into iron oxide, the reddish-brown, flaky substance we call rust. In this process, the iron atoms lose electrons. They are oxidized. Those electrons are then picked up by oxygen atoms, which become reduced. The result is iron oxide, or rust. The rust isn't just a surface stain, it's a sign that a fundamental chemical transformation has occurred, one electron at a time. Other redox reactions are far more energetic. Combustion, for example, is just a very fast oxidation reaction. When you burn wood or gasoline, the carbon and hydrogen in the fuel are rapidly oxidized by oxygen, releasing a great deal of energy as heat and light. It's a chaotic and beautiful process, driven entirely by the rapid transfer of electrons. But redox isn't just about things breaking down or burning, it's also how your body generates energy. Inside your cells, a process called cellular respiration breaks down glucose from the food you eat. During this process, electrons are stripped from the glucose molecules and passed down a series of proteins in what is called the electron transport chain. This controlled flow of electrons powers the production of ATP, the cell's main energy currency. Oxygen is the final electron acceptor at the end of this chain, which is why we need to breathe. Without oxygen to catch those electrons, the entire system would grind to a halt. This carefully orchestrated flow of electrons is beautifully similar to what happens inside a battery. A battery is essentially a portable, contained redox reaction. Inside, you have two different materials, an anode that readily gives up electrons, it gets oxidized, and a cathode that eagerly accepts them, it gets reduced. When you connect the battery, electrons flow from the anode to the cathode through the circuit, powering your device. It is silent, reliable redox at work. Rechargeable batteries use reversible redox reactions. When you charge them, you are using electricity to push the electrons back to where they started, resetting the system. Photosynthesis is another vital redox process. In a green leaf, light energy is used to split water molecules. Electrons are pulled away from the water, oxidation, and are used to help convert carbon dioxide into glucose, reduction, storing the sun's energy in chemical bonds. It's essentially the reverse of cellular respiration. Instead of burning sugar to release energy, the plant uses energy to build sugar. In both cases, electrons are on the move. In the lab, redox reactions are used for things like electroplating, where a thin layer of metal is deposited onto an object to make it shiny or protect it from corrosion. Many water treatment systems use redox reactions to neutralize harmful contaminants. Even the little strips in a blood glucose meter use a tiny redox reaction to measure sugar levels. The substance that loses electrons is called the reducing agent because it causes the other substance to be reduced. The substance that gains electrons is the oxidizing agent because it causes the other substance to be oxidized. It's a kind of reciprocal chemistry where nothing happens in isolation. What makes redox reactions so compelling is that they are truly everywhere. They power life, industry, and nature. They can be slow and creeping, like rust on an old fence, or unimaginably fast, like a spark igniting a gas stove. They can be beneficial, like the energy we get from food, or destructive, like corrosion weakening a bridge. But they all come down to one simple, elegant process: electrons finding new homes. Every redox reaction is a story of change, of atoms adjusting their balance, and of systems shifting in a quiet, constant pursuit of stability. In the grand theater of chemistry, most of the attention goes to the big players: the atoms reacting, the bonds breaking, and the energy being released. But tucked quietly behind the curtain are the unsung heroes that make it all happen, faster, smoother, and with far less effort. These are the catalysts, the quiet helpers of the molecular world. They don't take center stage, they don't change themselves, but without them, many of the reactions essential for life and industry would move so slowly they might as well not be happening at all. At its core, a catalyst is a substance that speeds up a chemical reaction without being consumed in the process. It's a sort of molecular matchmaker, helping reactants find each other and encouraging them to get on with the business of bonding. Once the reaction is finished, the catalyst steps away, unchanged and ready to facilitate the next one. It is the ultimate enabler, efficient, discreet, and quietly indispensable. A catalyst works by providing an alternative pathway for the reaction, a shortcut with a lower activation energy. The result is that the reaction can happen more quickly and under milder conditions, without needing to raise the temperature or pressure. It's like finding a secret side street to bypass a traffic jam. You reach the same destination, but the journey is much faster and requires less fuel. Catalysts come in many forms. In industry, metals like platinum and palladium are used to catalyze everything from making plastics to processing fuel. In your car's catalytic converter, these metals help transform toxic exhaust gases like carbon monoxide into less harmful substances like carbon dioxide. But the most elegant and astonishing catalysts of all are found inside your own body. They are called enzymes. Enzymes are biological catalysts made of proteins, and they are astonishingly good at their jobs. They can speed up reactions by factors of millions, turning slow, lumbering chemical processes into lightning-fast transformations. Without enzymes, your body would simply not work. Digestion, cell repair, energy production, all of it relies on enzymes working around the clock. Each enzyme is highly specific, usually working with only one particular molecule, called a substrate. The enzyme has a specially shaped pocket called the active site, which fits the substrate like a glove. When the substrate binds, the enzyme holds it in just the right position to help break or form bonds efficiently. Once the reaction is complete, the new products drift away, and the enzyme is ready for the next substrate. It's like a molecular assembly line where the workers never tire and everything runs with perfect precision. A classic example is the enzyme catalase found in nearly all living cells. Its job is to break down hydrogen peroxide, a harmful byproduct of metabolism, into harmless water and oxygen. A single molecule of catalase can convert millions of hydrogen peroxide molecules every second. It's chemistry on fast forward. Another star enzyme is amylase, found in your saliva, which starts breaking down starches into simpler sugars the moment you start chewing. Enzymes are sensitive to their environment. Changes in temperature or pH can alter their shape and cause them to stop working. This is why a high fever can be dangerous and why your body works so hard to maintain a stable internal state known as homeostasis. The chemistry of life is balanced on a knife's edge, and enzymes are at the very center of it all. Outside of biology, catalysts are critical in manufacturing. The Haber-Bosch process for making fertilizer relies on an iron catalyst. Without it, we would not be able to produce enough food to feed the world's population. In fact, it's been said that half of the nitrogen atoms in your own body were fixed from the air by this process, made possible by a humble metal catalyst. In the field of green chemistry, catalysts are essential for making processes more sustainable. By lowering energy requirements and reducing waste, they help make chemistry more efficient and less harmful to the environment. They are the quiet force behind a more responsible way of doing science. Once you start noticing them, you realize that catalysts are everywhere. They enable change without changing themselves. They make the impossible seem routine. They accelerate progress without ever stealing the spotlight. It's hard not to admire that kind of quiet confidence. In a world where most reactions require heat, pressure, or brute force, catalysts are the smooth operators, slipping in, nudging atoms into place, and gliding away before anyone even notices. They're chemistry's backstage crew, making sure the stars shine as brightly as possible. And they remind us that transformation can come from gentle nudges, subtle shifts, and quiet, behind-the-scenes brilliance. Water is, without a doubt, one of the strangest and most wonderful substances on Earth. It is also one of the most essential. It covers most of our planet, it fills the air as vapor, it flows through our veins, and it makes up the bulk of every cell in our bodies. And yet, for something so completely familiar, water is quietly full of mysteries. It bends the rules of chemistry, defies expectations, and holds our world together with an elegance that is all too easy to overlook. At a glance, water seems simple. H2O, two hydrogen atoms bonded to one oxygen atom. But this tiny V-shaped molecule is anything but ordinary. Its peculiarities are the result of its shape, its polarity, and the special bonds it forms with its neighbors. Let's start with polarity. A water molecule is polar, meaning it has a slightly positive end and a slightly negative end. The oxygen atom is more electronegative, so it pulls the shared electrons a little closer, giving it a partial negative charge and leaving the hydrogen atoms with partial positive charges. This makes the water molecule behave like a tiny magnet. This polarity is the heart of water's personality. It allows water molecules to attract one another through hydrogen bonds. These aren't true chemical bonds, but rather strong attractions between molecules. Yet, they are powerful enough to give water a collection of remarkable and life-sustaining properties. Hydrogen bonding gives water its unusually high boiling point and its strong surface tension, the property that allows water to bead up and lets insects walk on its surface as if on an invisible film. It also gives water cohesion, the ability to stick to itself, which helps pull water up from the roots to the leaves of the tallest trees. Water also has a very high heat capacity. It can absorb a vast amount of heat with only a small rise in its own temperature. This is why coastal climates are often milder than inland ones. The ocean acts as a giant thermal buffer, absorbing heat in the summer and slowly releasing it in the winter. It is nature's temperature manager, keeping our planet's climate within a tolerable range. Here is another of water's strange tricks. It expands when it freezes. Most substances become denser and shrink when they solidify, but water does the opposite. As it freezes, its hydrogen bonds lock the molecules into an open, hexagonal crystalline structure that takes up more space than the jumbled arrangement of liquid water. This is why ice is less dense than liquid water and why ice floats. The consequences of floating ice are enormous. If ice sank, lakes and oceans would freeze from the bottom up, making most aquatic life impossible. Instead, ice forms an insulating layer on the surface, protecting the liquid water below and allowing ecosystems to survive harsh winters. It is a quirk of molecular geometry that ends up preserving life itself. Water's role as the universal solvent is another of its superpowers. Its polar nature makes it incredibly good at dissolving other polar and ionic substances. When you stir salt into water, the individual sodium and chloride ions are surrounded and gently pulled apart by the water molecules. This is why nutrients can travel through your bloodstream, why plants can draw minerals from the soil, and why cleaning with water is so effective. However, water is not good at dissolving nonpolar substances, like oils and fats. This is why oil and vinegar separate in salad dressing. It's also why soap is so useful. A soap molecule has a polar end that binds to water and a nonpolar end that binds to grease, allowing the oil to be carried away by the water. Inside your cells, water is the medium in which thousands of chemical reactions take place. Enzymes, DNA, and proteins all fold and function within a watery environment. Water helps to stabilize their structures, shuttle ions across membranes, and even participates directly in some reactions. Water also plays a starring role in photosynthesis, where plants use sunlight to split water molecules. The oxygen released during this process, the very oxygen you are breathing right now, comes directly from the water that plants absorb. Every breath you take is a quiet echo of water's generosity. On a planetary scale, water helps to sculpt landscapes through erosion, move heat across the globe through ocean currents, and shape our weather through the continuous water cycle. Chemically, water is stable but not inert. It can act as both an acid and a base, making it a crucial participant in maintaining pH balance in living systems. In the search for life beyond Earth, the search for liquid water is central. Water may not guarantee biology, but it seems to be a necessary ingredient. It is a solvent, a temperature regulator, a transport medium, and a reactant. It doesn't just support life, it enables it. On a personal level, you are more water than anything else. Your blood, your brain, even your bones contain water. It cushions your joints, regulates your temperature, and delivers nutrients to your cells. And yet, for all its importance, water is often overlooked. But once you begin to pay attention, it becomes clear just how strange, clever, and vital this little molecule really is. Water is a rule bender, a shapeshifter, and a quiet alchemist that holds the secrets of chemistry in a single silent drop. Matter, at first glance, seems like such a simple thing. It is the solid stuff of the chair you're sitting on, the invisible air you're breathing, and the wan liquid in the cup beside you. But beneath these everyday appearances, matter is in a constant state of motion, shifting between forms, vibrating with energy, and occasionally undergoing beautiful transformations. Understanding the states of matter is like peeking behind the curtain of physical reality, where we find a graceful dance of particles responding to the gentle cues of temperature and pressure. Traditionally, we learn of three basic states: solid, liquid, and gas. Adding plasma gives us the full classical quartet. Let's wander gently through these familiar states to see what makes them tick. We'll start with solids, the quietest of the bunch. In a solid, particles are arranged in a fixed, orderly structure, like people sitting in assigned seats in a theater. They don't have the freedom to roam, but they are not completely still. Each atom or molecule vibrates gently in its place. Solids hold their shape because the particles are tightly bound together by strong forces, resisting change until enough energy is added to loosen their grip. If you introduce heat, the particles begin to vibrate more vigorously. At a certain point, called the melting point, those vibrations become strong enough to break free from the rigid structure. The particles don't fly apart, but they begin to slip and slide past one another. The solid has become a liquid. Liquids are the social middle ground of matter. The particles are still close together, but they can now move and flow. A liquid will take the shape of its container, but maintains a fixed volume. The molecules are in constant motion, bumping into one another and rearranging themselves, but still held together by gentle intermolecular attractions. If you add more heat, the particles move faster still. Eventually, they reach the boiling point, the temperature at which they have enough energy to break free entirely and escape into the air. The liquid becomes a gas. Gases are the wild spirits of the particle world. Their particles are fast, far apart, and largely independent of one another. A gas will expand to fill any container it is in. The air in a room is made of gas particles constantly bouncing off the walls, each other, and you. Because the particles are so far apart, gases are highly compressible. You can squeeze them into much smaller spaces. But what if you keep adding energy, far beyond boiling? The gas particles can gain so much energy that the electrons are stripped away from their atoms. What you're left with is a superheated soup of charged particles, free electrons and positive ions. This is plasma, the fourth state of matter. Plasma might sound exotic, but it is the most common state of matter in the visible universe. Our sun and all the stars are giant balls of plasma. Lightning bolts and the beautiful auroras are also plasma in action. Now, let's go the other way. As you remove energy, particles slow down. A gas will cool and condense into a liquid, like dew forming on the morning grass. A liquid will slow down further and freeze into a solid, as water turns to ice. Sometimes matter can skip a step. Sublimation is when a solid turns directly into a gas without becoming a liquid first. Dry ice, frozen carbon dioxide, does this, creating a dramatic rolling fog as it vaporizes. The reverse process, deposition, is when a gas turns directly into a solid, which is how frost forms on a cold window pane. All of these transitions are phase changes. They don't alter the identity of the substance, just its form. Ice, liquid water, and steam are all still H2O. The only difference is the amount of energy their molecules have and how free they are to move. Energy is the key player here. Temperature is a measure of the average kinetic energy of particles, how fast they are moving. Pressure influences how close they are forced to be. Together, these two factors determine the state of a substance. Ultimately, understanding these states is about recognizing that matter is always in flux. At the particle level, everything is in motion. Matter is never completely still. It is alive with energy, just moving at different speeds. There is something profoundly comforting in that. The tea cooling beside you is losing energy, its molecules slowing down, relaxing into stillness. The air in your lungs is a gas, flowing in and out with every gentle breath. All around you, matter is shifting quietly, following the timeless rules of thermodynamics, a soft rhythm unfolding endlessly in every corner of the universe. Not every combination in chemistry ends in sparks, explosions, or dramatic transformations. Sometimes things just mix. They swirl together, settle into layers, dissolve, or float, and that's that. No new molecules are formed, no bonds are broken or created. This quiet kind of chemistry, the realm of mixtures, solutions, and suspensions, is every bit as fascinating. It is the everyday blending of substances that keeps your morning tea flavorful, your salad dressing separated, and the ocean salty. A mixture is not a chemical reaction. In a reaction, atoms rearrange to form entirely new substances with new properties. But in a mixture, the components retain their original identities. They are simply sharing the same space for a while. A key hallmark of a mixture is that its components can be separated by physical means, like filtering or evaporation. Mixtures generally fall into two categories: homogeneous and heterogeneous. A homogeneous mixture is uniform throughout. You cannot see the different components. Salt water is a great example. When salt dissolves in water, the sodium and chloride ions disperse so evenly that the mixture looks just like pure water. In contrast, a heterogeneous mixture is one where the parts remain separate and visibly distinct. Think of a bowl of soup with vegetables, or a vinaigrette dressing where oil floats on top of vinegar. The components are easily identified and do not blend uniformly. A solution is a specific type of homogeneous mixture where one substance, the solute, is completely dissolved in another, the solvent. In salt water, salt is the solute and water is the solvent. Solutions can exist in any state of matter. The air we breathe is a gaseous solution of nitrogen, oxygen, and other gases. An alloy, like brass, is a solid solution of metals. But not everything dissolves. Oil and water famously resist blending because oil is nonpolar while water is polar. Water molecules would rather stick to each other, so the oil is excluded, forming a distinct layer. This brings us to another type of mixture, a suspension. In a suspension, small particles are mixed into a fluid but are not fully dissolved. These particles are usually large enough to make the mixture cloudy and will eventually settle out if left undisturbed. Muddy water or orange juice with pulp are both suspensions. They need to be shaken or stirred to remain mixed. Somewhere between solutions and suspensions lie colloids. In a colloid, tiny particles are evenly distributed but not truly dissolved. The particles are small enough that they don't settle out, but they are large enough to scatter light. Milk, mayonnaise, and fog are all colloids. They often appear homogeneous to the naked eye, but behave differently from true solutions. Your favorite salad dressing is a classic example of an emulsion, a type of colloid where oil droplets are dispersed in vinegar. On their own, they separate. But if you add an emulsifier, like mustard or egg yolk, it helps to stabilize the oil droplets, keeping the mixture creamy and unified. In the kitchen, physical changes like mixing, grinding, or melting are part of the daily chemistry of food. They change the arrangement of molecules, but not the molecules themselves. Compare that to a chemical change, like baking a cake. Here, heat causes new compounds to form as sugars caramelize and proteins denature. The result is something entirely new, and the process is irreversible. Because the substances in a mixture retain their properties, you can often separate them using simple physical methods like filtration or evaporation. Even crude oil is separated into gasoline, diesel, and other products through fractional distillation, a process that sorts substances based on their different boiling points. In nature, mixtures play essential roles. Blood is a complex suspension of cells in plasma. Soil is a heterogeneous mixture of minerals, organic matter, and water. Seawater is a solution filled with salts and gases. And this brings us back to one of the most calming realizations in chemistry. Not everything needs to react. Sometimes things just coexist. Molecules can float alongside each other, mingle, and remain themselves. Mixtures are about balance, between blending and staying distinct, between change and stability. They remind us that chemistry isn't always about big transformations. Sometimes it's the quiet, gentle beauty of things simply coming together. Some chemical reactions happen so fast you barely notice them, a match flaring to life in an instant. Others unfold with the patience of a mountain, like ire slowly rusting over many years. Whether it's a rapid blaze or a slow decay, every chemical reaction proceeds at a certain pace. This pace is known as the reaction rate. It tells us how quickly reactants are converted into products and reveals how willing molecules are to make a change under certain conditions. One of the biggest influences on reaction speed is temperature. In most cases, increasing the temperature speeds up a reaction. Heat is energy, and when you raise the temperature, you give molecules more of it. They move faster, collide more often, and hit each other with greater force. More frequent and more energetic collisions mean more opportunities for bonds to break and new ones to form. This is why food spoils faster on a hot day and why cooking relies on heat to transform ingredients. But it's not just about bumping into each other. For a reaction to occur, molecules have to collide with enough energy to overcome the activation energy barrier. By heating a system, you increase the proportion of molecules that possess this necessary energy. Concentration is another key factor. The more reactant particles you have crowded into a given space, the more frequently they will collide. A concentrated acid will react more quickly than a diluted one, simply because there are more reactive particles available to interact. It's like increasing your chances of finding something by looking in more places at once. Surface area also plays a powerful, if sneaky, role. For reactions involving a solid, only the particles on the surface can react. If you increase that surface area, you speed up the reaction. A single sugar cube dissolves slowly in tea, but if you crush it into a fine powder, it disappears almost instantly. The powder has a much greater surface area exposed to the water. This is why powdered substances can be so much more reactive than their solid counterparts. But sometimes, even with high temperatures and concentrations, a reaction is still naturally slow. This is where catalysts step in. As we've learned, catalysts provide an alternative pathway for the reaction with a lower activation energy. They are like taking an escalator instead of climbing the stairs. You reach the same destination with far less effort. Enzymes in our bodies are master catalysts, allowing the reactions of life to occur at an incredible speed. Light can also influence reaction rates. In some cases, photons of light provide the energy needed to initiate a reaction. This is the first step in photosynthesis, where sunlight strikes chlorophyll and triggers the cascade of reactions that create sugar. In modern chemistry, understanding and controlling reaction rates is crucial. Chemists carefully tweak conditions, adjusting temperature, pressure, and concentration, and choosing the right catalysts to find the sweet spot where a reaction is fast enough to be useful, but controlled enough to be safe. Even in cooking, you are constantly manipulating reaction rates. Browning meat involves the Maillard reaction, which happens quickly at high temperatures to create delicious flavors. Let the pan get too hot and you burn the food. Keep it too cool and it remains pale. Refrigeration, on the other hand, is all about slowing down reaction rates. The cold temperature slows down the chemical and biological processes that cause food to spoil, preserving it for longer. Some reactions are so slow on a human timescale that they seem not to be happening at all, like the geological processes that turn ancient organic matter into oil and gas over millions of years. Others are incredibly fast, like the combustion inside an engine, happening in a fraction of a second. Understanding reaction rates is about understanding time in the language of chemistry. It's recognizing that every molecule is in motion, constantly colliding and deciding whether to stay the same or become something new. The rate at which these choices unfold is influenced by the world around them. Every bubbling pot, every rusting hinge, every ripening peach is a slow ballet of molecules interacting at their own unique pace, a pace that matches the gentle rhythm of the world around them. Biochemistry is the soft-spoken cousin of big, flashy chemistry. It doesn't erupt into fireballs or fizz over in dramatic swirls. Instead, it hums gently in the background, quietly managing the countless reactions that keep you alive every second of every day. It is chemistry in a cardigan, practical, efficient, endlessly detailed, and essential in the most fundamental way. Without biochemistry, there is no heartbeat, no memory, no breath, no thought. Every blink, every yawn, every dream is powered by the tidy, tireless work of molecules behaving just right. At the heart of biochemistry are a few key players: proteins, DNA, and ATP. These molecules are the stars of the show that plays out inside every living cell. Their power comes not from showmanship, but from consistency. Life doesn't need wild reactions, it needs reliable ones. Let's start with proteins. These are the workhorses of life itself. Proteins are long chains of amino acids folded into fantastically complex three-dimensional shapes. The shape of a protein is everything. It determines its function. A protein might become an enzyme, a biological catalyst, a structural support, a transporter, or a signal messenger. Enzymes, as we've learned, are crucial for speeding up the reactions of life, allowing digestion, cell repair, and energy production to happen on a timescale that can sustain us. And what about DNA? Deoxyribonucleic acid is the grand architect of life, the molecule that stores all the instructions for building and operating an organism. It's a beautiful double helix, a twisted ladder made of just 4 kinds of chemical rungs, or bases. The sequence of these bases forms the genetic code, the blueprint for building all the proteins your body needs. But having a blueprint isn't enough. The cell needs energy to carry out the instructions, and that's where ATP comes in. Adenosine triphosphate is the molecular currency of energy. It's a small, rechargeable molecule that powers nearly every biological process. When a cell needs to do work, contract a muscle, send a nerve impulse, or build a new molecule, it spends an ATP molecule by breaking one of its high-energy phosphate bonds, releasing a burst of energy. All of these reactions and thousands more make up what we call metabolism. Metabolism is a vast, interconnected web of chemical pathways, all happening simultaneously, all finely tuned to maintain balance or homeostasis. There are catabolic pathways, which break down complex molecules to release energy, and anabolic pathways, which use that energy to build new molecules. It is a constant, balanced cycle of breaking down and building up. You can think of metabolism like a bustling city. Molecules are zooming around, being processed in factories, by enzymes, and powered by fuel stations, ATP. And somehow, through all the motion, nothing crashes. The system is exquisitely regulated by feedback loops and signaling molecules that keep everything flowing smoothly. Take glycolysis, the process that begins the breakdown of glucose to extract energy. Instead of breaking glucose down all at once in a burst of energy, the cell breaks it down in a series of 10 small, controlled steps. Each step is catalyzed by a specific enzyme, and the energy is released in manageable packets, much of which is captured in the form of ATP. This slow, steady process is far more efficient and safer for the cell. Sometimes things do go wrong. A genetic mutation might lead to a malfunctioning enzyme, causing a metabolic disorder. A misfolded protein can lead to disease. These conditions offer a glimpse into just how carefully balanced life's chemistry really is. And yet, life is also remarkably resilient and adaptable. One of the most astonishing things about biochemistry is how universal it is. The same basic processes, the use of DNA, proteins, and ATP, occur in nearly every living thing on Earth, from the simplest bacterium to the largest blue whale. Life doesn't reinvent the wheel, it refines it. Biochemistry is the chemistry of stability. While other branches of chemistry might aim for speed or transformation, biochemistry is all about sustainability. It's how life takes a humble pile of atoms into movement, thought, feeling, and memory. And it does so without exploding, which, when you think about it, is truly incredible. You are made of atoms that follow the same rules as those in rocks and stars, but in you, they assemble and react in ways that produce not just order, but consciousness. You don't feel it, you don't hear it, but it's there, a molecular symphony playing just beneath your awareness, a whispering choreography of proteins, enzymes, and tiny sparks of ATP, all working together in the quiet dark to keep the lights on and the gears turning. At the heart of biochemistry are a few key players: proteins, DNA, and ATP. These molecules are the stars of the show that plays out inside every living cell. Their power comes not from showmanship, but from consistency. Life doesn't need wild reactions, it needs reliable ones. Let's start with proteins. These are the workhorses of life itself. Proteins are long chains of amino acids, folded into fantastically complex three-dimensional shapes. The shape of a protein is everything. It determines its function. A protein might become an enzyme, a biological catalyst, a structural support, a transporter, or a signal messenger. Enzymes, as we've learned, are crucial for speeding up the reactions of life, allowing digestion, cell repair, and energy production to happen on a timescale that can sustain us. And what about DNA? Deoxyribonucleic acid is the grand architect of life, the molecule that stores all the instructions for building and operating an organism. It's a beautiful double helix, a twisted ladder, made of just 4 kinds of chemical rungs, or bases. The sequence of these bases forms the genetic code, the blueprint for building all the proteins your body needs. But having a blueprint isn't enough. The cell needs energy to carry out the instructions, and that's where ATP comes in. Adenosine triphosphate is the molecular currency of energy. It's a small, rechargeable molecule that powers nearly every biological process. When a cell needs to do work, contract a muscle, send a nerve impulse, or build a new molecule, it spends an ATP molecule by breaking one of its high-energy phosphate bonds, releasing a burst of energy. All of these reactions and thousands more make up what we call metabolism. Metabolism is a vast, interconnected web of chemical pathways, all happening simultaneously, all finely tuned to maintain balance or homeostasis. There are catabolic pathways, which break down complex molecules to release energy, and anabolic pathways, which use that energy to build new molecules. It is a constant, balanced cycle of breaking down and building up. You can think of metabolism like a bustling city. Molecules are zooming around, being processed in factories, by enzymes, and powered by fuel stations, ATP. And somehow, through all the motion, nothing crashes. The system is exquisitely regulated by feedback loops and signaling molecules that keep everything flowing smoothly. Take glycolysis, the process that begins the breakdown of glucose, sugar, to extract energy. Instead of breaking glucose down all at once in a burst of energy, the cell breaks it down in a series of 10 small, controlled steps. Each step is catalyzed by a specific enzyme, and the energy is released in manageable packets, much of which is captured in the form of ATP. This slow, steady process is far more efficient and safer for the cell. Sometimes things do go wrong. A genetic mutation might lead to a malfunctioning enzyme, causing a metabolic disorder. A misfolded protein can lead to disease. These conditions offer a glimpse into just how carefully balanced life's chemistry really is. And yet, life is also remarkably resilient and adaptable. One of the most astonishing things about biochemistry is how universal it is. The same basic processes, the use of DNA, proteins, and ATP, occur in nearly every living thing on Earth, from the simplest bacterium to the largest blue whale. Life doesn't reinvent the wheel, it refines it. Biochemistry is the chemistry of stability. While other branches of chemistry might aim for speed or transformation, biochemistry is all about sustainability. It's how life takes a humble pile of atoms and turns it into movement, thought, feeling, and memory. And it does so without exploding, which, when you think about it, is truly incredible. You are made of atoms that follow the same rules as those in rocks and stars, but in you, they assemble and react in ways that produce not just order, but consciousness. You don't feel it, you don't hear it, but it's there. A molecular symphony playing just beneath your awareness. A whispering choreography of proteins, enzymes, and tiny sparks of ATP, all working together in the quiet dark to keep the lights on and the gears turning. The Earth may seem like a solid, steady place, a big rock floating through space, but beneath its surface and above its clouds, our planet is a restless, dynamic chemical system. It breathes, cycles, and changes constantly. The mountains erode, the oceans shift, and deep below, molten rock simmers in silence. From its churning core to its icy poles, the Earth is always reacting. Geochemistry is the study of this planetary scale chemistry, the story of rocks, water, and gases over vast stretches of time. Let's start deep underground. The Earth's interior is a hotbed of elemental drama. A core of iron and nickel is surrounded by the mantle, a thick layer of semi-molten rock that churns in slow-motion convection currents. These currents drive plate tectonics, causing the continents on the thin crust above to drift, collide, and slide past one another. Volcanoes are one of the most striking examples of geochemistry in action. Magma from deep within the Earth contains dissolved gases like water vapor and carbon dioxide. As the magma rises and the pressure drops, these gases bubble out of solution, like opening a shaken can of soda. These expanding gases can drive explosive eruptions, hurling ash, rock, and lava into the air. But these eruptions also play a vital role in cycling elements. The gases contribute to the atmosphere, and the minerals in the lava slowly break down, enriching the soil. Once those volcanic rocks are on the surface, they begin a new chapter, weathering. Weathering is the gradual breakdown of rocks. Chemical weathering occurs when water, oxygen, and acids interact with the minerals in the rock. For instance, rainwater is naturally slightly acidic because it absorbs carbon dioxide from the atmosphere, forming weak carbonic acid. Over thousands of years, this gentle acid can dissolve entire limestone formations, carving out vast caves and intricate underground rivers. It is chemistry with immense patience. One drop at a time, it transforms mountains into sediment. The dissolved ions released by weathering make their way into rivers and eventually the oceans. This is why the oceans are salty. These ions also provide essential nutrients for marine life. Calcium and carbonate ions, for example, are used by corals and shellfish to build their calcium carbonate shells. When these organisms die, their shells sink to the ocean floor, eventually becoming compacted into limestone rock. This is a key part of the carbon cycle. The carbon cycle is one of the most important chemical cycles on our planet. Carbon moves between the atmosphere, oceans, land, and living things in a complex, interconnected loop. Photosynthesis pulls CO2 from the air. Respiration and decomposition release it back. The burning of fossil fuels releases carbon that was buried for millions of years. The ocean absorbs huge amounts of CO2 from the atmosphere. It's a grand planetary cycle with a very real influence on our climate. The atmosphere itself is a reactive soup of gases. The ozone layer in the upper atmosphere protects us from harmful UV radiation. Greenhouse gases like carbon dioxide, methane, and water vapor trap heat, keeping our planet warm enough for life to exist. The balance of these gases is delicate and is what determines our global climate. Through all of this, the Earth behaves less like a static ball of rock and more like a single integrated system with feedback loops and self-regulating processes. The composition of the atmosphere affects the temperature, which affects the rate of weathering, which affects carbon levels in the ocean, which then loops back to influence the atmosphere again. It's chemistry with memory, cause, and consequence. We are not separate from this planetary chemistry, we are a part of it. The atoms in our bodies are borrowed from these great geological cycles. The calcium in your bones was once part of a rock. The nitrogen in your DNA may have been fixed by lightning in a prehistoric sky. And the carbon you exhale will one day be food for a tree. So when you step outside and feel the breeze or watch the clouds drift by, know that you are witnessing chemistry in its slow, magnificent stride. The Earth is not just a place we live, it is a vast, breathing laboratory of elements in perpetual, silent motion. Chemistry isn't just something that happens on Earth. It also unfolds in the great, open silence of space, between the stars, inside of them, and in the long, cold stretches where barely anything seems to move. Out there, where gravity reigns and light takes millions of years to travel, chemistry is hard at work, shaping galaxies, planets, and even the very atoms in your body. It is a slower, more cosmic kind of chemistry, but it follows the same fundamental rules. Let's start in the most dazzling laboratories of all, stars. These enormous balls of plasma are powered by nuclear fusion, a process where lighter elements, like hydrogen, are crushed together by immense gravity and heat to form heavier elements, like helium. This process releases the vast energy that makes stars shine. But fusion is also a form of elemental alchemy. In the cores of massive stars, the process continues. Helium fuses into carbon, carbon into oxygen, and so on, building up heavier and heavier elements in layers, like a cosmic onion. This continues until iron is formed. Fusing iron consumes energy rather than releasing it. At this point, the star can no longer support its own weight. Gravity wins and the star collapses in on itself, triggering a spectacular supernova explosion. In the heart of that explosion, for a brief, brilliant moment, all the elements heavier than iron are forged: gold, platinum, uranium, and more. All of this material is then hurled out into space, seeding the cosmos with the raw ingredients for new stars, new planets, and eventually, life. It is not just poetic to say that we are made of stardust, it is a chemical fact. The carbon in your muscles and the calcium in your bones were born in the hearts of stars that lived and died long before our solar system ever formed. Between the stars lies the interstellar medium, filled with vast, cold clouds of gas and dust called nebulae. These are the stellar nurseries where new stars are born. Within them, atoms and molecules drift, collide, and sometimes stick together on the surfaces of tiny dust grains. Gravity slowly pulls denser regions of these clouds together, forming new stars. Even in these frigid, near-vacuum conditions, complex chemistry occurs. Astronomers have detected over 200 different molecules in space, including water, ammonia, and even simple organic molecules like alcohols and sugars. These are the prebiotic building blocks of life, suggesting that the raw ingredients for biology might be widespread throughout the galaxy. As stars age, they recycle their matter back into space, enriching the interstellar medium with the heavier elements they created. This cosmic recycling is how the universe has grown more chemically diverse over time. Closer to home, the atmospheres of the planets in our solar system showcase their own unique chemistry. Venus has a thick atmosphere of carbon dioxide with clouds of sulfuric acid. The gas giants, Jupiter and Saturn, have swirling clouds of ammonia and methane, and Saturn's moon Titan has lakes of liquid hydrocarbons on its surface. Even comets, icy wanderers from the outer solar system, are frozen time capsules of the solar system's early chemistry, containing water, carbon dioxide, and organic compounds. In the growing field of exoplanet research, astronomers are now able to analyze the light passing through the atmospheres of distant planets to detect their chemical fingerprints, searching for signs of water, oxygen, and other potential biosignatures. All of this reminds us that chemistry is the universal language. Atoms come together, break apart, and reassemble across billions of years and billions of miles. You are not separate from that story. You are a chapter in it. The iron in your blood and the oxygen in your breath were all forged in stars, passed through the cold of interstellar space, and woven into the living being that is you. The chemistry that built you also built the galaxies. So when you look up at the night sky, you are seeing a reflection of yourself scattered across the stars. Even in the quietest moments, chemistry is never truly still. A cold cup of tea, a breath drawn in the dark, the gentle creak of wood in a settling room. Beneath it all, atoms are in motion. Molecules shift, electrons dance, and forces balance. It is a rhythm far too small for us to see and far too constant for us to hear, but it is there, all the same. Every moment, every object, every part of you is held together and changed by the slow, steady, and sometimes spectacular poetry of chemistry. Over the course of this journey, we have wandered through the vast and varied world of matter, from the tiniest atom to the fires of distant stars, from the slow rust on a garden gate to the lightning-fast reactions inside your cells. We have seen chemistry move with speed and sound, but we have also explored the calm chemistry, the kind that unfolds with immense patience, weathering stone, dissolving sugar, or folding a protein with exquisite precision. We began with the atom, the smallest building block, full of character. We followed the elusive electrons and saw how their drive for stability leads to the formation of bonds, giving rise to the endless diversity of the world. We explored how energy drives reactions, how catalysts can offer a gentle shortcut, and how acids and bases change the mood of a solution. We watched matter shift through its states: solid, liquid, gas, and plasma, each revealing a different kind of motion and freedom. We saw that not everything needs to react. Sometimes things just mix. We explored the quiet, tireless chemistry of life inside our own bodies, where proteins, DNA, and ATP perform a silent symphony. And finally, we stepped beyond ourselves, into the chemistry of the Earth and the cosmos, finding our own origins in the hearts of dying stars. What all of this reminds us is that matter is never dull. It may appear motionless, but at the microscopic level, it is always humming with invisible action. Stillness, it turns out, is full of life. There is something profoundly comforting in that thought. We live in a world that often values speed and spectacle, but chemistry tells us that slow, quiet change is just as powerful and often more lasting. Behind every one of these reactions is a story, a tiny narrative about atoms wanting to be stable and systems seeking equilibrium. It is a chemistry not just of things, but of tendencies and probabilities. The periodic table is not just a list, it is a cast of characters, each with its own quirks and preferences. The chemistry of water is the chemistry of your blood. The chemistry of carbon is the chemistry of your thoughts. The chemistry of light is the chemistry of sight. It is not separate from us. It is us. So as we come to the end of this journey through the chemistry of nearly everything, I hope you have felt the wonder that lies just beneath the surface of the everyday. I hope this has been interesting, but not so interesting that it has kept you from your rest. If you are still peacefully listening with your eyes closed, I would love to know where in the world you are tuning in from. What time is it where you are? Are you curled up in bed or on the couch with a pet? Let me know in the comments. I love hearing where this chemistry journey has taken you. And if you enjoyed this exploration, if you found it relaxing or gently thought-provoking, please consider giving this video a like or subscribing to the channel. It helps me bring more of this content to you and lets me know that these gentle dives into science are bringing a little more wonder into the world. Thank you so much for being here and for joining me in this quiet celebration of how the universe works, one invisible reaction at a time. And remember, even when nothing seems to be happening, chemistry is always happening. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, is still beautifully, endlessly alive. Good night.